we've gone over. If you've got some quad that's in ax squared plus bx plus c, that's your general form. You get your vertex or turning point by doing negative b over 2a, and then plugging that in to get the y value. This is just on one of those tabs on your foldable. The second formula, or way to give out a quadratic, is the one on the right-hand side. If you've got that, you can easily tell what your vertex or turning point of the parabola is, and you can see whether or not it opens up or down. And then the last one, in all honesty, is the biggest bear we may have all year. It's an alternate form of your quadratic. It's asked all the time. And it's asked because not many people are good at it. I went through and instead of doing our like Algebra 2 sort of notes that can be convoluted at times, or I guess go too deep, we're going to give you, these are the straight Math 165 Introduction to Calculus or Advanced Pre-Calculus U of R notes. That's what you have for today. It's not going to be that tough. I think you can handle it completely. The only thing that you've got to remember is down here in green are the last two forms of your quadratic equation. To figure out which one of these two forms you're going to be applying, you've got to look at which variable is being squared. If the y is being squared and not the x, if the y is what's being squared, then the parabola is going to open left or right. If the x is what's being squared, your parabola is going to either open up or down. You probably have not seen it presented this way. We'll show you some justification for this alternate definition of a parabola. But actually, it's the same definition we've been using the whole time. You're going to have three critical values to plot, or three critical items to plot to graph out a parabola in this form. You've got a focus point, which is the point in the center of your parabola. You have a vertex point, which will be a max or min that the graph goes through. And then you have a directrix, which is a line directly behind your parabola, or below it, depending on how you view it. And we're going to have something called a p-value. The distance from the vertex to the focus is the p-value. That same distance going the other way gets you to the directrix. So if I go up 3 units from the vertex to get to the focus, I would go down 3 units to go from the vertex to the directrix. So your parabolas now can open any of the 4 ways. And if you haven't signed into your calc, please do so. We're going to show you how you can graph these odd parabolas that aren't functions. The y-squared parabolas aren't functions. We'll give you a minute to get this down. We'll show you actually why you need this. Do any of you have, how many of you have, I guess, Dish or Direct TV? 1, 2, 3, okay, 4, 5. You probably then have what on your house and or yard? What? Yeah, you got a dish on side. So you got a dish. Can you just sort of put that dish anywhere? Yeah, you can't put it in the basement. You've got to have that dish, and I can't even tell you, you guys are lucky enough, because aren't they small now? They're like, relatively speaking, they're tiny. When I was growing up, my grandparents used to have a satellite dish that was literally a satellite dish. Like, it was the size of a car in their backyard. And it was, like, the new ones are like a matte gray color. They're kind of like the, I don't know, like the iPhone back of it. It's like a silver, but not shiny. There's, I think, imagine a car in your backyard covered in aluminum foil all year long. Is it going to be a little bit bright? Yeah. Yeah, and I remember my grandparents actually, I think that they just told them that they needed to move. But if you were in my grandmother's kitchen, and she was an Italian grandmother, so she sat in there the whole time, it almost looked like she was going to get a tan, because there was so much intense light coming off of this satellite in the neighbor's backyard that she probably could get a tan. She had to go over and actually say, you need to move it. Now, the new ones are much nicer. They're not big. I think is it fair to say that they're probably the size of this desk? About that big. And they're like a gray. They've got a little arm, though, that comes out of it. And what shape is the back, I guess, or the non-armed part of it? Kind of like a dish. It's a circle, but it's concave, meaning it collects. Now, and they always tell you, you've got to move it. And then, once in a while, I guess the complaint about satellite TV versus cable or coaxial TV is what? What do they say on the Time Warner commercial? In a storm, God forbid, like we're living in like Tornado Alley or something like that. So once in a while, if there's a storm, you don't get a signal. Now, the reason you could lose signal in a storm isn't because there's a storm. It's because what's happening? Clouds, there's some sort of blockage to go through in there, which is why they always go out of their way to make sure that it's on top of the roof, not the side, because you don't want any blockage that way. And what about if there's trees or something? They try to stay away from that. The whole reason that you need that is, okay, algebra in motion. So here's the interesting part of it. This is the applied application piece of these. You're going to actually see these all over the place. The satellite dish one, though, we take from this one here. Now, if you go in, the reason, watch what happens, I guess, if your satellite dish is there, you know how it's got that arm on it? That arm should be at or around the center. Every point along the dish was constructed to reflect everything back to that one point where the center is, which would be right here. So even if the signal's coming in and needs to go here, if we made it to be that the signal needed to directly hit that object or that like signal in the middle in order for you to get cable, you only have a very limited spectrum. You have a very sort of bad picture reception. This lets you collect tons of beams to get sent up. This is what it really looks like. Now that's the image going out. You can see it. Watch what happens as it comes back. That's all those images. And then the dish collects them, puts them all, and they all reflect into the same spot. So that's why you're going to have some of those beams that are getting sent out. Some of them might just be for individual channels. Some of them might be to display like a band of channels. Whatever it is, that information, though, is getting sent out to you, and it needs multiple sources convening in. Does it ever work out on satellite that you'll get some channels and not all of them? Or does the whole system shut down if it's not getting its signal? Who's got this? Does it cut out frequently or no? Okay, so it's not even that big of an issue. Okay. So my only question was, if it does cut out, I didn't know if it was from a lack of individual signals or from display. Some of it, the system as a whole, my guess would be, wouldn't work if it wasn't getting enough signals from every person. But that's why you need a parabola like this. Another reason that it comes up, we don't have one, I don't think, here, but you've probably seen, what's a gigantic structure that looks like that one? You've got the Golden Gate Bridge. That was done in the 30s and 40s, which makes it, believe it or not, much less of an impressive industrial feat. The most interesting bridge, and I think it's one of the oldest ones, is the Brooklyn Bridge, which looks exactly like this. And it was built, I want to say, well before the Golden Gate Bridge. I think it was like early 1900s. This is a lot of engineering that's happening here that you guys probably wouldn't see. Why are these cables here? What do they help do? Distribute out that force. Like, as you're going through, it's not natural for you to lay out a piece of wood over a river and to be able to walk over it. What happens is you walk over that piece of wood without any support. It bows and almost makes a parabola. You actually are putting parabolas in to make sure this doesn't parabola. So you need all this. Anytime this gets pulled, now imagine you're right here. This is when it would be under the most stress. If you're here, you're not pulling down. You can't. Where does all of your force down get transferred to? Up on this beam. And then where does that beam connect to? Well, this giant parabola which is then going to pull down. And as that's pulling down, it starts pulling both of these in. So why doesn't the bridge just fold on itself? You've got anchors on the other side, which also happen to be what shape? Okay? So parabolas are incredibly efficient at naturally distributing out force. It's really important to, and that's a big concept. If you had done this straight across, and this needed to pull from here, that's when the ends would get pulled in. It's sort of that angular pulling piece of it. I don't know how much they've done with you in the past, but if any of you are interested in any form of architecture, it is so worth it to continue on with as much math and as much calc as you can. You'll come up with way better design than other people. I think, did we do it? Actually, I don't think we did it here. Who's been to Chicago before? Who's seen that giant teardrop, the reflective teardrop that they have in one of those parks? The beam? Is that what it's called? Yeah, the beam, right, because you can go underneath it. Who's seen that? Okay? Just so we're clear, the city of Chicago bought that. That's literally nothing more than a conic section, which is what you're working on here. And I want to say that the city of Chicago, the artist that built that, built it, and I want to say that the city of Chicago bought it for like $3 or $4 million from them. So imagine being an artist. Now, granted, you have to put this whole thing together. You made a reflective beam for $3 million. Right? Yeah, and the thing that makes it so impressive, Chicago didn't realize this when they put it in. They just thought it was really cool. The entire outside, imagine like a beam, like a kidney bean, sort of tilted upright. So it kind of looks like, I don't know, you can sort of pass underneath it. I'll show you a picture in a minute. It's not by accident, though. Chicago actually lucked out. The whole surface of that is reflective. So, who were people who were there before? What did you notice was hanging out around the base of that, like a pest? There used to be a lot of hanging around. You didn't see a bunch of people doing that? It came out before they had iPhone cameras all over it. But now, everyone goes there for one of two reasons. You get to see it, but it's not just enough for you to see it. You have to take pictures of it to let other people know that you also saw it. And then they share those pictures. Now, he was a genius when he created it, or this team, this architect team made it. Because from every angle, you get to reflect out and see the city. At no point, unless you're literally looking up to the sky, would your picture reflect out the sky. So all behind you, you're the city. If you're in charge of tourism from Chicago, everyone goes and takes their picture in front of this thing. And what do they see behind them? The city of Chicago. And then people go, that's kind of weird. Where did you go to see this? And then you say, what? Chicago. And they go, oh, maybe we should go to see that same thing at Chicago. And then when we're there, because they took a picture to show us that they went, you know what we should do when we go? We should take a picture so they know then that we went there. See how much more full our lives would be. We had done that. But we'll suffer over here in silence. Now, I'll see if I can find this picture that was being in a minute. Is a class field trip? Yeah, it's probably fair to say. Yeah, and that's it. We can all take your individual. And then, just remember, individual pictures only can make like 2 or 3 people jealous of this one. Can you imagine if we took a picture of all of us together? Can you imagine how envious everyone would be? And they would know that we were better than them because we had gone to a place that had a giant reflective surface on it and took our picture when it was sunny. Wow. Now, we're going to go through, for our work today, there are some of you who are formula people, and I don't begrudge this to you in the least. But for our formula kids, I always give out everything. If you need the formula stuff, that's how you find it. It's so much easier to actually just do the problems out and conceptually understand instead of being enslaved by these formulas. We've got to find the focus and the directrix of this parabola. First thing up, I've got to ask myself, look at my given. Is that a parabola where the x is squared and the y is squared? Take a look at what's there. look, is this an x squared parabola or a y squared parabola? And when I go through and look, what would I go through and see? Jack, what would you say? Is it an x squared or a y squared parabola? So since it's y squared, which directions could this open? It could open left and it could open right. I'm going to go to the margin here. My generic form is this: y minus k squared equals 4 times p times the quantity x minus h. And remember, hk is your vertex. Now look at our equation. So that's the one we've got. I always like to put our equation right underneath it, which would be y squared equals, in this case, 8x. So we've got a bunch of stuff missing. First thing up is, who can tell me what my k value is going to be? Hands up, please, when you can tell me what the k value is. Align it, make it match the other form. Your k value is going to be 0. What is your h value going to be? 0. So far, we're to here. We know that this is really telling you y minus 0 squared equals. Now, here's where it gets awkward. I need to recognize that this technically is 8 times, in parentheses, x minus 0. So this would be 8 times x minus 0. Does our current equation match up with our form from above, yes or no? If that's the case, watch everything you can now tell me. Oh, and Jack, you told us before, I didn't write it down. Which directions could this open? We know it could open up either left or right. And the way you figure out which one of those it's going to be is to go back and look at the p-value. Look at what's there. Know your p-value is 4 times whatever is in front of, 4 times your p-value gives you whatever is in front of that x minus h situation. So what is the p-value? And when you give it, tell me its sign. We've got 1, 2, 3 of them. Okay? So I list out my p-value is positive 2. Now, since p is positive 2, which direction out of those two do you think it would open if the p-value is positive? Take a guess. We're going to say it's going to open to the right. So I can even eliminate this choice. You also know what your vertex is. What did we say were the coordinates, Sophia, of the vertex, or what's your h and k? So I know it goes through 0, 0. So now, you need to give out the directrix and all of that. It works so much nicer if you just start drawing. First point you can always give is your vertex, or well, that we can give as our vertex, because you know, what's your vertex? What's its coordinate? So here's my generic xy axis. At the origin, 0, 0, and I'm going to write v, 0, comma, 0. That way you know it's the vertex. Now, we knew this graph was either going to open left or right because it's a y squared. We know it's going to open right because the p-value is positive. How far to the right do I need to go before I hit the focus point? 2 units over. So I'm going to go 2 units to the right. I'm going to put a dot there, and then I'm going to put an F above it. What are the coordinates of the focus? Ryan Smith, what will they be? Now, you've done everything out perfect so far. Your parabola, if you want to draw it now, you even can. Opens like that. What did we not go through and state yet, though, that we still need to go through and state? Which is a line behind the parabola. How far did I move to go from my vertex to my focus? Emily, what did you say? How far did you move from your vertex to your focus? How many units? No, from the vertex to your focus, that was your p-value. How many squares over did you go? 2. So now you've got to go back to and sketch the line there. It's going to be a vertical line, meaning it goes up and down. I hope we can get this. You can tell me what my directrix equation would be. Take a look at what's there. It's always awkward because it's when it's these, you're like, oh, it's 50-50. For some reason, you always pick the wrong one. Yeah. That is your directrix. X equals lines go up and down, Y equals go side to side. So, I guess what is our focus point going to be if you needed to list it out again? Sam and Kate, what would you say? What's your focus point? What's your vertex? And what is your directrix equation? Perfect. Notice there's symmetry there. I didn't show it to you in the other one because I wanted you to get used to actually listing it out. Where did our geo sketch go? There we go. So we've got this that we can give. Here's another way of viewing them, and we'll Conic. Okay. So I'm not quite sure how much they did with shapes with you and other classes. Here's the stuff that we're going to talk about, and I'll give you the brief background on it. You're going to see this again when you get to tweak out this out. This right here is what shape? A cone. Everything that we go through in graph can be represented as a section or slice of a cone. That's why you'll hear it's called a conic section. If this is my cone, if I wanted to cut this so I could get out a circle, hands up please when you can describe to me what cut I would do on this cone to go through and be left with a circle. Got 1, 2, 3, 4. How could I trim this down? Yeah, it's got to go flat across. It needs to be, technically the definition of it is it's got to be parallel to your base. It's a plane that's parallel to the base. If I do that, you get a cut like this. And what shape is our cut? What does it leave us with? Circle. Now, if I want an ellipse, hands up if you've looked at an ellipse before. Okay, it's a circle with 2 centers. How would I go through and create an ellipse on this? What would I want to go through and do? Yeah, I'd want to take a diagonal cut, something like this. So is that an ellipse? Now you've got 2 left to do. One of them you haven't dealt with before at all, and one of them you have. You have not dealt with, you actually have dealt with hyperbolic motion, whether you admit it or not. The one that you should know is parabola. How could I cut this shape, this cone? Describe to me the cut I would have to take in order to be left with a parabola as the exposed face. What do I need to go through and do? Yeah? Yeah, it's going to have to intersect the base. There's actually one little bit of nuance to it. Yeah, it's got to be perpendicular to that base. It has to be a vertical cut. Now, when we do that, you get, oh, wait a minute, sorry. Not vertical, slightly angular, but it has to intersect. If you do the vertical, that gets you your hyperbola. Here, there you go. What shape is that? That's your parabola. If you do it going up and down, because technically there's a second cone on top of this one going up and down, like 2 cones that meet at a point. In physics, it helps explain like gravity apparently somehow. Yeah. But if you go straight up and down, you get 2 of them. Here's what conic sections are. The one you'll have trouble with, or the one we're going to work with, is the parabola. So you've got this guy here. Those are your cuts. Hopefully you see this is how an ellipse is generated. See how it's a circle with 2 centers? What happens the closer I bring those 2 points together? What do you think is going to, how's that going to impact the shape of your ellipse? It's going to get more circular. It's going to have a higher eccentricity, which is an approximation to circular motion. Has any of you taken astronomy, or have you looked at planetary motion yet? And earth science, you look at it? So understand, all of the planets travel in what type of path? An ellipse. It's not a circular orbit. It's an elliptical one. And the reason that happens, not only does the planet have gravity pulling it in from the sun to keep everything sort of in place, it's just that the sun is the loudest one. Like, you know how, I guess there's other things that exert forces on us to pull us in certain directions. Everything from, I guess, our own gravity to the gravity of the sun pulls us in. You also have, like, other planets exerting gravity. But one of the things that's kind of cool is when you look at hyperbolic motion. Have any of you seen Apollo 13 before? Raise your hand if you've seen Apollo 13. Really? Great. Who's familiar with what happened in Apollo 13? What happened? What ended up happening, and keep in mind this was like in the 60s, so you were like 40 years away from having 40 years away from a smartphone. The computer that is in your calculator right now is 40 times more powerful than the computer they had to throw them out of Earth towards another planet that doesn't have oxygen. So you kind of be a little bit nervous. And while they're out there, they went to dock with another something that was out in space. And it ruptured the gas line and took away a lot of their power as they were drifting towards the moon. Now, I don't want to scare you at all, but who's going to come and get you and save you? Like, you call AAA if you're aimlessly drifting towards the moon? No. And by the way, the other part, why did America take so much, why did we really go crazy on making sure someone went to the moon? Yeah, we were, not space invaders, but there was an arms race between us, the United States, and the Soviet Union. At the time, they went through and got someone to outer space first, which literally led to there being a dramatic change in public education. They're saying, our kids, why don't American kids learn? Why is it that Russian kids are able to go through and get that into outer space? Well, the fact of the matter is, Russia did it like 70 times and just never told us about the 70 people that died when they were trying it. America was kind of open about things, so we let people know. We were 1 for 1. They were 1 for like 80. Right? But we were second, so we sort of lost it. We needed to get out there. We sent our people out to the moon so we could market for ours, even though it's literally another planet. So we go out to the moon, except they didn't have a way even to get back besides that one method. So what ended up happening as they were drifting along, they figured out we've got no gas. So what we're going to do, so here's the moon, here's Earth. You were going out towards it. They recalibrated, got really close, and almost intentionally crashed into the moon. Just like on a roller coaster, if you go around a circle, if you go around a corner, it has sort of a force multiplier on it. It seems faster. You're accelerating while you remain at the same speed. You're accelerating speed while remaining at the same, your velocity is increasing because velocity looks at speed and orientation. So you're getting faster just because you're turning. It's the same reason if you spin around in one of those chairs, you get dizzy. They slingshotted around to go through and make that happen. They went through after these people, and keep in mind, did they have a computer to line up their orbits? No. So they were doing all this by hand. And the thing that was amazing, under the best case scenario, if you rerun what happened to them as a computer simulation, they live 10% of the time. Is that a lot of the time? No. Would you might have had an accident in your spacesuit if they called you up and said, hey, we need you to use centrifugal force to get you back to Earth because we don't have any more gas for you. Would you be a little bit nervous? Yeah, I would be super nervous. So that's one application of hyperbolic motion. What you're going to do today with parabolic stuff is actually kind of easy, but it is. Go in right now, do out this next one underneath it. Would you please list out that next one underneath it? What are we missing today? Where did it go? Yep. Save. Good. Remember, the focus is on the inside. Now, for the first term up, I guess the only part of this that should be a little bit awkward is figuring out what that p-value is. If you don't currently have anything sort of next to it, if it's not inherently given, recognize you have to factor out and cause the x to have a leading coefficient of 1. So if you do that, that may mean you have to divide something out. That lets you see that what your 4 p-value is. As I'm listing this out, our p-value in this should come out to be how much? Positive 4. Which direction is this parabola then going to open? To the right-hand side. It would look something like this. You've got a point here in the middle. Your focus is at 4, 0. Your directrix is behind you. And that line would be x equals -4. What is your vertex? 0, 0. Do we have questions on that? There should be symmetry there. The last type, I guess, that we're going to go through and look at, we may come back to this example. I want to make sure we get to one of the more challenging ones. Actually, slide over, please, to page 2 and do the second one down there. Just find the standard form of that. Read what's there, and I want you to start graphing out what's there. You're given your focus, you're given your directrix. What else can I find if I'm given those two items? We got 3 people, 4. Gavin, what can you go through and get that would be helpful for your picture? We've got the focus given in the in the directrix. And where would the vertex be? Yeah, it's going to be halfway between those two. So I label that V, 0, 0. Which direction is this parabola going to open? Andrew? Nope. It's going to have to open up. The reason that it's going to have to open up, if it opened to the right, it would go through the directrix, and we can't have that. If it opened down, it's going through the directrix or to the left. Now, when we're listing this out, I hope we should be able to get this one. Let's start off with, Matthew, would you go through and say, is this an x squared or y squared parabola? Okay, so I go in and fill out x minus h squared equals 4 times p times y minus k. What can you fill in to that equation right now? And what's your, keep going. Yep, so this means I have x squared is equal to something times y. He's right, he said that there's zeros. What's our p-value in this? Hands up, please, if you can tell me that. What do you think the p-value would be? 1/2. So what's 4 times the p-value? 2. Oh, is it positive or negative 2, by the way? Or positive or negative 1/2? Positive. Why would it be positive? Opens up. Anything up or to the right. Now, here's the one that you're going to get that's probably going to be a little bit difficult. And we can even maybe cross out. Go, please, over to page 3. We're going to try the second one down together. Hang on. Sorry, I want to make sure I'm doing a good one. 8y to be 1. That. 7 and 8, that would be plus 1, 7, 1 gives you 8. What's my other one? Oh. One on the other 3. I just want to find one that we can do to make it a little bit more. So, yeah, let's do this one. So, sorry, I'll give you, I wanted space for you to work. Go to the last one on page 2 at the bottom. I just wanted space for you to work. As it stands right now, you're going to get this into that conic form where you can easily see the focus, directrix, etc. So when we're looking at this, first thing up, is this a y squared parabola or an x squared? Which one? So I'm going to write out the y squared formula, and now your job is to make ours look like this. So it would be y minus k squared equals 4p times the quantity x minus h. Notice, on the left side, there's all y's. So that's what we're going to need to have happen first. Look at the original. I want all my y's together on one side. So if I did that, I'd have y squared minus 6y. What would I be left with then on the other side when I got my y's isolated? We've got 1, 2 of us. What would be on the right-hand side if I got my y's isolated? Sarah, what would you say? Perfect. It's now 2x minus 8. Questions on how we got to there? You all, when you were in Geo last year, did a process called completing the square. Raise your hand if you recall it. Okay? I'm going to teach it as though you hadn't had exposure before. The reason why, I can give you a shortcut that makes it even more sort of autopilot and less thinking. Your goal is to make this on the left be something that looks like this. Something times itself gives me this. The way to get there, hopefully easy, is as follows. First step is our lead coefficient on our squared term of 1. Yes. Look at your b value. In this example, what's our b value? -6. Raise your hand if you're confident, and I'll say without the calculator. Who is smart enough to take half of -6? Hands up, please, if you can do that. Don't go to the calculator. You've got 3 of us, 4. Half of -6 without the calculator. Without. Not bad. Not bad. Now, instead of discarding that, I write that up here. It's small, not part of the work, but part of our doodles. Take half of your b value and write it down. Then remember what we do next. We got 1, 2, 3, 4. Not bad. What do you want to say? When you say it, what's that? Square -3. What's now? I better not do one bit of class. We're going to take -3 and square it. Don't go to the, you can do it. Are they going to know? She believes in you guys. Let's see. No. Nope. -3 squared. You gave me the square root of it.
9. What's 9?
Careful. Just the 9. Now, we needed that number. Look on the left side. You did this for a reason. What will the left side become? This is a manufactured outcome. You made this happen. It's not by chance. Look at the left. How will you rewrite out the left-hand side? Oh my God. You've got y squared minus 6y plus 9, and we've got 3 people, 4. How could you rewrite that out? It is screaming to be done. Screaming. Screaming. If it's good scream. Maybe it is screaming. Give me one second. Now, it's almost as if, now you're going to write y minus 3 being squared. Remember how you wrote out this number here? That's always the same. Did they show you that or no? Now, as I'm doing this out, you should, and this is another thing that is outrageous. I'm offended by all of you right now. Outraged and offended at all of you both individually and as a whole right now. I should be dodging shoes right now. You should be ready to throw your desk at me. You should be absolutely and utterly disgusted with the work that's up there. You should be so mad. You should be ready. Who would you complain to? You should be ready to write to Mr. Benz, write to your senator, write to your congressman. This is a travesty. Outrageous. And I'm outraged at you. for not being outraged at me? You're outraged. Who is outraged? Which what? You're going to hit me with the stick or stab me with a wooden stick? Maybe both. No! That would be if it was that y squared minus 9. What? You can't just randomly start adding 9s to half of an equation. Hello? You've got to undo it, which means after I list this out, now on the right-hand side, you would go through and have a positive 1. It's not in the form we need it to be just yet. And this again is where you will fall apart because of you don't trust yourself or you bail because it possibly could look slightly awkward. Right now, have I factored it such that my x has a coefficient of 1? Yes or no? What do you need to factor out to make that happen? A 2. Now, stop saying, you can't do it. There's the other one. You can't take a 2 out from a 1. You absolutely can. There's a fraction. Now, looking at this, think of all the stuff you can now tell me. Let's start off with what's your vertex, taking a look at what's there. Sam Morgan, what would you say your vertex is? So, now I'm not going to graph it, but I could say my vertex is going to be, what'd you say it was? Negative 1/2, comma 3. Next thing that we would need to go through and do is figure out which direction this is going to open. Before I do that, I need to figure out my p-value. Take a look at what's there. Hands up, please, if you can tell me what p's value is in this quadratic. What would we go through and say p's value ends up being? Got 4 of us. Is it? Of course it is. We got 4 times the p, that's equal to. Now, we've got choices for opens. This is a y squared, so which directions could this open? Left or right? Which one will this open? To the right. Now, there's no magic to find anything else. Start section. You've got a vertex at negative 1/2, 3. I don't know, here's some axes, negative 1/2, 3. Boom. That's my vertex. Negative 1/2, 3. Next thing up, I've got to go 1/2 over to the right, put a dot there, that's my focus. What's the coordinates of the focus going to be? Hands up when you can tell me what your focus coordinates are going to be. You had to move the p-value over to the right. That's it. 0, 3. How can I figure out what my directrix is? Yeah? No. No. There you go. It's not a number, it's an equation, and it's x equals negative 1. How'd you know it would be negative 1, or why'd you place it there? You should, and the reason that I tried to bring this other file up, I think it's open now. So we talked about this. Here is, watch what now, in ours, what was it an x equals on ours for the last one? For the directrix, is that right? Okay, so if our directrix is vertical, watch what happens to the focus point, which is, well, watch this relationship. See how these are 2 squares and this is 2? If I take my focus and make it go out to 3, oh, I don't think I can move it. I'll move this instead. What happens to your focus as I move the directrix away? Notice that's preserved, though. If I go out 6 spots, the focus goes out 6 spots. And by the way, if I go this way, notice what happens the whole time. It works if you go. We did vertical, now let's do horizontal. Drag it down, that's what you get. The further away it is, the greater the p-value, the wider the graph. The narrower it is, the narrower the graph, and so on. There's one more that we always go through and say. It's a little bit awkward because uh, maybe you're too young to think it's funny. There's, as of right now, you've only got 1 point on the graph that you can go through and give. You've only given 1 coordinate on the graph. What's the only thing that we go through and give that's actually on the graph? The vertex. So in order to give a parabola, though, you can actually give out 3 points. This distance that you went from here to here is your p-value. The other thing that you should be able to do, see how right now you're at your focus? If you go out 4p in length on, I guess, 2p on each side, you'll get other points. So how long was this distance here? How many? Well, I'll do this. I'll make it go up so I'm not worried about negative. Oh, sure. So how long was this distance from your vertex to your focus? How big was that distance? 2. Multiply that by 4, and what do you get? 8. So that means there's a bar going side to side through the focus that's 8 units long. That's also on the graph. So that means if this whole thing is 8 long, how far would I go on each side? 4. So you'd have an extra point there and an extra point there. That helps you see how the graph takes hold. Now, the part that's awkward, that length is called latus rectum. And everyone always says, no one, okay. Once in a while you get a chuckle because rectum is like intestines and whatever. Okay, so if you need to let that out, you can go through and own it. But understand that gets you 2 more points. The state never tests on it, but you're going on to pre-calc and calc, so it's something you should kind of know. We're going to do one more where we manipulate the equation, and then I think we're done for the day. Take a look. Let's do the second one. Actually, let's do the one at the top of page 3. That way you'll give yourself a little bit more space. Now in this case, oh, is that a y squared one? You didn't cross that last one out. I guess the next one an x squared? Yeah. Sorry, let's do the one underneath it just because it's an x squared. I don't want you to think they're always y squared. So that's the equation we've got. This one is an x squared, so I'm going to make mine look like that. I've got to have it in x minus h squared equals 4p times y minus k. Ours doesn't look like that, so I'm going to bundle the x's together and everything else to the side. So when I do that, I have x squared minus 2x, and then on the other side, what is it going to be, 8x plus 7? 8y plus 7. From here, what's our next step going to be? Now, can you do that without the calc or no? What do you got? What do you do? And by the way, I'm going to write out a -1. Hands up if you can tell me what we do after we give out the -1. And what do you got? So I'm going to put a +1 here and here. That leaves me on the left. You should know what this factors to automatically. What does the left factor to? The quantity x minus 1 being squared. Now, on the right-hand side, I'm not doing too much at once. I've got 8y. I'm going to combine like terms. Remember, when we add 1, you've got to do it to both. Does my y have a coefficient of 1? How will we make that happen? Thankfully, we avoided fractions. All right, this is an x squared parabola. Which direction could it open? Up or down? What's our p-value? My p-value is 2, so that means my parabola is going to open. And what is your vertex on this? Or is it 1, -1? So, I mean, if we needed to, you've got to graph that. All right, x, y, 1, -1, so go over 1, down 1, put a dot there. That's my vertex. Focus, I'd have to go, what, up 2? So your focus is 1, 1. Your vertex is 1, -1. What's your directrix going to be? Y equals -3. Look at how much you know. Now, before you go, your homework is at the back of this. I just want to show you this before you start freaking out. Look at question A. Is question A for your homework tonight, is that in the right form? Is the squared term alone? Look at A. Is the squared by itself? No. What do you need to do to get the squared by itself? multiply by 8, which means this becomes, multiply everything by 8, which would mean this is x squared equals 8y. Can you go back now and do that? Yeah. What about the next one? Is that in the right form? Is your squared term alone? So what do we have to multiply by? Negative 12. So that leaves me what? Y minus 2 quantity squared equals negative 12x. I mean, can you handle that?
I don't know. Work out.
And yeah, I gave you the space to go through and do it. I'm sorry that I did 2 on 1 page. It was easier to do that than to put the homework on your own. So make sure, please, that we know that. I'm going to tell you that. Well, make sure, please, you know that. If you get this done, you'll be in good shape. I'm going to send out the answer sheet to the homework. If they give it to you at times in an alternate form, understand you can always manipulate by multiplying or whatever. Do your algebra on it to make it match the form we need. There's more than one form that's accepted. This is probably the easiest stuff. All right? Now, and actually, I got from you guys your green packets the other day, correct? Did you see, there was a bunch of grades added the other day from your Math Excel, is that right? We've got more. I don't have your tests graded just yet. Hopefully tomorrow. I got one section of calc exams and then yours. I guess the very last thing, make sure you know those formulas when we come in tomorrow. All right? We should be in a good spot. Oh.